I focused on margin architecture, segmentation, and the continent-ocean transition related to breakup both in the Northeast Atlantic and also in the South Atlantic. This year, I will have more focus on the importance of linking the offshore and onshore crustal scale structure. And we need to do so to have better constraints for quantification and restoration of pre-drift extension. And we will also see a few examples that the geometry of the crustal thinning across the margin is closely related to the topography onshore adjacent to the margin. So let's start up in the Northeast Atlantic. Here we show the present day database for deep seismic refraction data. So you see all across the Norwegian margin, it's covered by a dense grid of wide angle seismic data. And in the background, you see the coverage of the multi-channel seismic reflection data, which means it's completely covered. And now it's an increasing coverage of 3D seismic as well. While on the conjugate Greenland side, it's a bit harder to acquire data because it's still covered by ice much of the year. But there's an increasing numbers now with the data on the conjugate side, also utilizing the fjords that we have in East Greenland and also some onshore geophysical experiments. So if we, based on the available data, put together some regional transect that takes us from one side of the ocean to the other. The ocean here is younger than 55 million years after Greenland moved away from Eurasia during opening of the Northeast Atlantic. And by that, we can put together conjugate transects that starts way into mainland Norway on the eastern side and ends up on the Greenland side. And having these kind of profiles, we see clearly how the crust is thinning due to a number of rift phases prior to breakup and then during breakup. And we would like to restore these kind of profiles by taking out the young ocean to understand the basin setting at the time of breakup. So this is a profile from Norway to Greenland in the northern part of the Northeast Atlantic. In the southern part, it's a bit more complex because there we also have a microcontinent sitting in the middle of the ocean. But in both cases, we can do the restorations and come up with a pretty straightforward closure of the oceanic basin. From the present day, as you see here, we can quickly go 55 million years back, and then we see how the sedimentary basins on the Norwegian margin lines up with what's at the present day Northeast Greenland margin before it enters into the Eurasian plate again in the Barents Sea. The color-coded polygons here represent sedimentary basins that formed within the plate prior to breakup in response to a number of rift phases. So we would like to look into more detail how we can continue to restore these effects of extension. So we have now closed the ocean, but we would like to go pre-drift, quantify the extension, and restore it. And to do so, we have to look into the broader plate tectonic evolution of the Atlantic. And we already see that if you go to the present state-of-the-art models that you can find, for instance, in G-plates or other plate reconstructions, all agree how we close the ocean. But then we clearly start to disagree where to put Greenland in a pre-drift context. So what we are aiming at now with the database we have at hand in the Northeast Atlantic is to put together a number of conjugate crustal transects with the Norwegian side, on the right-hand side here, the Greenland side. So we have removed the oceanic part, and we look at the geometry of crustal thinning. How can we estimate the amount of extension? Well, first we do is to go directly on the observables. And that's why we really need to have transects that takes us all the way up to onto the mainland, where we can be pretty sure that way into Norway here or Greenland here, there's been little thinning in response to these phases of extension-based information. So we need a sort of reference thickness of the crust. In our case, it's around 35 kilometer. And then we see moving out on the margin how we systematically thin the crystalline part of the crust from more than 30 to less than 10 kilometer. And we can also see by looking at different conjugate transects that we have asymmetry across the ocean, and we have also lateral variability along the margins. The thinning factors direct from observations compared to a reference thickness of, let's say, 35 kilometer can be compared to estimates of extension from tectonic basin modeling, where we do both forward in time and reverse time modeling to see how we fit the basin configuration and the subsidence of the sedimentary basins. In addition to the amount of extension, we need to see in what direction, the orientation of the extension, and we are in particular interested to see where these tectonic hinge zones are located when we start to restore the margin evolution. And of course we need to have edge control as well, the timing of the extensional events. So we have done this on a number of profiles. Of course this type of modeling is more time consuming, but with good constraints we can do it. As I said, both forward modeling and backstripping and restoration. This is an example from north of Norway, where we have very deep sedimentary basins, as deep as 15, 16 kilometers, where we have had a severe extension during the late Mesozoic Paleogene prior to breakup. Here we know that there has been at least 4 major rift events, and we also see from the forward modeling that to reproduce the present-day basin configuration, the crustal configuration, we have to extend the area here more than 225 kilometers. And that fits nicely with what we observed in terms of geometry of crustal thinning. So both the tectonic modeling forward in time and backwards in time compared to the direct observation give us a sort of stretching distribution, thinning distribution across the margin. And if we do that for all of these conjugate transects, we can come up with an extension estimates. Of course, there is one more challenge, and that is to compensate for the nature of the deep crustal body that we see in every geophysical transect across the Northeast Atlantic, this so-called lower crustal body, which some think is completely added material during the breakup magmatism, in other words, an underplate. There could also be intrusions into the lower crust, so there's some magmatic addition, but also some crustal host rock present prior to breakup. And regardless of what we use in terms of the reference thickness for the thinning estimates and the amount of magmatic addition to this system during breakup, we end up with extension in the order of 300 to 400 kilometers. And this we have to restore if we want to make proper paleogeographic reconstructions. That was the oil industry asked for, because they would like to have these paleogeographic reconstructions. They want to do source to sink scenarios. And I think we can provide that while starting with the closure of the oceanic basin. And then we go step by step. To the mid-Cretaceous, we remove the extension in the late Cretaceous Paleocene. We go to the mid-Jurassic and take away the amount of extension in the late Jurassic, early Cretaceous, and we can continue back to Permian. Taking out these 300 plus kilometers of extension, we suddenly see how close Greenland comes to Norway. And we also see suddenly that we have salt basins on both sides that lines up, which is another argument for making a well-constrained plate reconstruction. When we are dealing with deep basins on continental margins, when we are combining deep seismic reflection data with refraction data, it's very important that we carefully look at the deep basin configuration on the margin. Because we know from the flanks of the basin that we have thick sedimentary succession from prior to the main rift phases, but we have difficulties to identify them in the deeper part by seismic imaging, and we also have to rely more on the refraction data. But it's very important that we, in the deeper part of the basin, we put in a sequence that we know corresponds to sedimentary rocks, but it has been deeply buried. All the porosity is gone. So it's highly compacted, and it's also stretched or thinned by a factor 3 to 4. So if we, during reconstruction of such a profile, we take away the extension and decompact, suddenly we will see the sedimentary succession that we easily image on the flanks of the basin. If we put all this into basement, we have problems doing the reconstruction of the basin, because then we underestimate the effect of that compaction had on the subsidence. And with new data, we now are able to see more and more of the deep basin configuration. So we will see layered sedimentary units that falls within velocities above 6 km per second, which we usually from a refraction model turn into basement, but it's highly compacted sedimentary rocks. So this is something we have to bring with us to the southern part of the Atlantic, looking at similar conjugate profiles on the Brazilian margin and the conjugate African side, where we, some years back, only had rather good reflection seismic. And then we had to combine that with gravity modeling to put together crustal scale conjugate transects. But it's equally important here to get as far landward, onshore, on the Brazilian side and on the African side, to be sure that we look at basement that has its original thickness very little affected by the extension, thinning prior to breakup. This is an example from the Northeast Brazilian margin, where we some years back had reflection data onshore and offshore, but we didn't have wide-angle refraction data. So we had to rely on the results of gravity modeling to get a first-order crustal configuration. Now, recently, there have been acquired a lot of wide-angle data in this part of the Brazilian margin, and it's interesting to see how it more or less follow up on the first-order crustal geometry. It puts the continent-ocean boundary more or less in the same position as we had it in the previous data example. But we also see now the importance of getting coverage where the crust thickens, the base of the crust deepens, and to do so we really need recorders onshore, recording seismic waves generated by the air guns when we are acquiring wide-angle seismic in the offshore part. Of course, this is data from the so-called SALSA project that was published this year in a paper by large paper by Pinheiro et al. And a few years ago, there was also the first publications coming out based on the Samba wide-angle profiles, where we see equally the importance of getting onshore recordings to better image the very important transition from the ocean to the continent, where we see a dramatic thickening of the crust landward, and we reach nearly to areas that we can use as a reference when we do the crustal extension estimates for reconstructions beyond time of breakup, to really understand how the sedimentary basins here formed and initiated prior to breakup. There's also an interesting relationship between the crustal structure and topography. If you have been to Norway, you know that there's a lot of mountains both in southern and northern Norway adjacent to the continental margin. They are young, and to what extent they are directly related to breakup and margin formation. It's a matter of discussion, and also the importance of young erosion through the glacial history. But it's very clear that the highest topography in Norway sits in the south. Then there's a rather low relief in the mid-Norway around Trondheim, and then the high mountains again in the north. And it's also interesting to see when we compare the topography onshore to the overall crustal configuration. In other words, what's the distance from the area where we have a crust around 40 kilometer thick to the continental margin where that crust is thin to less than 10. That's typically what we call the taper length. When that is wide, we have rather low topography on the landward side. Where that taper length is small, narrow, we have much higher topography on the margin, on the landward side. And this is typically what we can see many places around the globe, where we, in this case, look at the Moroccan margin, rather low relief and a wide crustal taper, while off Namibia we have a much narrower, sharp transition and higher topography on land. If you put that together, data from many continental margins around the world, it looks like it's a clear relationship between the taper length and the topography on the landward side. So I think that's something we could also then add to further studies on the Brazilian margin to see how the geometry of crustal thinning in the offshore domain relates to the topography in the onshore part. And to do so, we should also start looking further into what's the width of that transitional zone from thick, unstretched crust to very thin crust underneath the inner part of the continental margin, to see whether we have the same variability along strike of the system. This is what we have found out to be the case for the Norwegian margin. I think there are also good reasons to believe that we are facing the same in the Brazilian margin. So, thank you.
And inside you have a very high topography. Seems to me that's not match very well with that model that you present.
Yeah. So I think that's we have seen the same in so many margins now that there's clearly one of the processes behind margin uplift. Of course, this is the flank to the rift. We see it's under development in the Red Sea today, for instance, and it's interesting to compare the two sides. Is it asymmetric? Is it something inherited from before crustal breakup? Of course, when we look at the margins up in the Norwegian part, we know that there's a very severe overprint by very young glacial erosion. So of course, if ice get away making valleys and fjords, of course that unloading creates more uplift. So we have a very important phase of young uplift. But people really interested in that also forget that there was something going on before, and that's related to the margin evolution as we see in most margins. Yeah. No. It's clearly, you saw when I closed the ocean that Greenland was sliding past Svalbard. So when this started, it was a big mountain belt in northern Greenland that also went to Svalbard. But the main reason for Svalbard actually being the Barents Sea geology exposed, that is, it is related to the young erosion made by the glaciers, but there's a very major contribution that underneath Svalbard, the mantle underneath the crust is hot because it's in connection with Iceland. So for the last 10, 15 million years, Svalbard has been up in the air. There's been volcanism for 10 million years in Svalbard, even in the Quaternary, very, very recent times. And it's still hot. If you drill a borehole on Svalbard, it's 40 degrees per kilometer, which is more than you should expect. So there is also some dynamic support from below. So Svalbard is a very special case. That's why we can go there and touch the rocks that we usually map out in the seismic.
But we're still trying to fix a technical issue with sharing screen. So while you're uploading your presentation, where did this have to go? Yes. Okay.
Brazil. Yes, this one. Yes. Okay. Good afternoon. I would like to thank HITSC for the invitation for this presentation. What I'll show is basically a proposal of a work to help in this big project that's been going on from University of São Paulo and people from Norway. I'm José Eduardo Soares. Okay. Oh. Good. Okay, here we are. Here we have some refraction experiments that you have carried on in Brazil during the last 15 years. And I will talk a little bit about the proposal of onshore works related to this experiment from Espírito Santo and Rio de Janeiro margins, located in the zone, and show some results that are related to some experiment conjugated with the Pabriz one that this data was acquired from my lab, the Labilitos. And then I will, in the end, show the results of this experiment and the conjugate profile of this both acquired, both refractions. Okay. Our proposal essentially passes for 3 points. One is to increase the onshore lines on land, install the seismic stations, probably 85 kilometers until 100 kilometers from the coast. These stations will work as offset shot gators to help to define the margin transition. I consider that it is not enough, and after that we'll complement this study with receiver function that can be able to sample the crust very close to the coastline. Okay, install BB, broadband and short period seismic 3XL stations for RF and RF surface wave joint inversion studies. These stations should be deployed as soon as possible once they have to be continuous working for 2 years. And the end, that is the final or the main part of the experiment, is to acquire your data, installing more 300 vertical stations to complement the 3XL station installed before, and shoot it 15 kilometers along the profile. And then this, what we intend to do. In the seismology case, we hope to obtain a section with depth of the borehole and crustal VPVS ratio, that is the Poisson ratio along the profile. With the joint inversion of P and P receiver function surface waves, we hope to have a model of S waves and crustal discontinuity along the profile, and with S receiver function, we intend to map or to help map discontinuity in the upper lithospheric mantle, with the emphasis to the lithosphere-stenosphere boundary. The war data what you can get from them, the PNS wave tomograph, and POAS ray tracing modeling. I consider that the refraction model, it brings to us mainly the behavior of the lower crust. That's very important, and we are talking about stretching crust, rework the crust, for example. And CCP inversion is a consequence of the wave field velocity, PNS, obtained in this data, and then seismization showing depth and geometry of the interface. I can show some example involved the 3 parts. This is the line that I received from Petrobras, from Marcos Toaldo. 1, 2, 3. What they are proposing is to increase the central line to until 700 kilometers to have a regional one, and to install stations along all of them, 3XL stations, each 25, 30 kilometers along the line, to obtain a first approach, and to really constrain the crust along the coast. And in the central line, we are putting 10 broadband stations from my lab. Okay. This data will allow us to obtain the geometry and velocity field of the upper crust, lower crust, and the lithospheric mantle under the profile. What happens? Lead to define borehole, the nature of the discontinuity under the profile, now with special interest to the coastal domain, to define the contact between the São Francisco Craton, Araçuaí and Ribeira belts, and the compositional affinity of the crust. With the Poisson ratio, can define if the rocks are felsic are transitional, are massive, and then can help to map and to understand the evolution of the crust under the profile. Just a minute, something wrong happened. Oh. Não tem teclado. Good. Nice. Thank you. Okay, and then now I will show some results from the seismology, applying to this array. I will show some results for this station and one profile crossing the Tocantins-Araguaia suture. That's contact from the Amazon Craton to the blocks that's east of it. Okay, and then there's a kind of result that can obtain. This from this station, the joint version, and then we obtain a model that can define upper, medium, lower crust, and the S velocity for the crust and for the upper mantle as well. This is a profile, and this one is a CCP from this profile, two different methods, but they are complementary. Okay, now I'll talk about the Fabrizio profile very quickly, I think, because you have a lot of data. And I will show the work that we did here. In the first moment, we deployed 3 axial stations for receiver function study. They used to stay work continuously for 6, 8, 9 months. After that, we complement the line with vertical sensors. This is a kind of sensor that you have from the PEG-BR from Brazil. We have almost 300 vertical sensors that you can use. Some view of the field work involve mainly students and people from the technicians, but people from the university and colleagues. The shots, and then you put the line of sensor, and you give a shot if 15 kilometers along the line. The shot is about hole. We put an emulsion of in the bottom part of it, and then we can pack with soil, and we used to shoot during the night. These shots, most of the time we are working with 1.5 tons for the shot. Okay. This is a sequence of processing receiver function, the first break tomograph, and then you can make a RF migration. After that, we have P-wave modeling obtained by ray tracing, S-wave modeling, and then you can return to RF migration and compare it to make the comparison between the models. This some RF results. For each station, you can obtain something like that. Here I have a very nice result with AT stack that permit me to have the depth of the crust, and the VPVS, the Poisson ratio. Putting all this data together, they give an idea for us how it is how moreholes is behaving, and more details inside the base as well. Here the multiples disappear, and this is due to the magmatism that's going up into the basin. Here we have the ore data set. I will show an example of the modeling, the main phases. This main phase modeling for one shot, for all of them, for the shallow part, for the middle, for the lower crust. I do not have mantle here with me, but we have a model, a P model. We do the same with S waves. This is a S seismogram related to P1. They are very similar in form. You can see. The PN, there is very weak SN, no reflection, surface waves. 1, 2, 3 examples. The ray tracing related to S waves. And then you can obtain with this data P, S in VPVS model. This is a kind of final model interpreted. The main points is that the crust was stretched in the central part. Our conclusion is the crust was delaminated in this close to the margins. The reason that is very thin related to this other part of the basin. In the lower crust, there is a presence of fluids, is what I define here. This is an underplating related to the central part of this basin and the stretch part. This is the final comparison between the model. Very interesting to see that this underplating appears here, not as a massive body mass, but as a, how I say, as a seal intrusions. Okay, change very simplified P. This is a EVAIN model that was shown for my colleague before, and putting both of them together, you have a profile that I would like to say from mountain to deep sea. Putting both of this profile together, you need to rearrange the coastal model, and the crust here is a little bit thinner than was proposed before. And in the end, is what we intend to obtain, or how you can collaborate with this project to obtain the seismic model for the onshore part. That's all that I have to present now. Thank you very much.
Thank you very much. Are there any questions? This one is not working. Any questions?
Soares, that image of the Paraná Basin has never been published.
What? Nothing's published yet.
Okay, so you say that there is a underplating in the beneath the.
You have a clear underplate because you have a very high velocity bore in the lower crust. But in the side as a roll, the mantle as well is drastically reworked. And it seems to me that you have inclusion for outside. This is what we're trying to express with a situation like this one. So we're very close to Paraná River. So the mantle here is a little bit different. And you have intrusions crossing the crust as well.
You think this can be inherited by the accretion of the different blocks that are beneath the Paraná Basin?
About the basement, we do not have any clear reference. I suppose to mark very clear difference with VPVS, with Poisson ration model. This part is a little bit different from this one, but close to the west part of the model was drastically intruded and modified in the Cretaceous, according to our interpretation. And then I don't know if it's part of this block or it's equal of this block or differentiate only the Cretaceous, or they have a completely different history. Excuse my bad English.
Thank you. Any question more?
Please, what range of frequency do you use in RF scale?
In RF?
Yeah.
In receiver function?
Yeah.
In the receiver function, we filter our data, you pass a low-pass filter of 2 hertz or something like that.
Mm-hmm, but
it's less than 2 hertz. In a receiver function, the word data, the refraction data, you pass a bandpass filter from 1, 2 until 10, 12 hertz. And then we work in this range of frequency.
Okay, thank you.
Okay.
All right. I think there are many more questions that could be asked, but I think in the interest of time we move on. Thank you. At least I had some questions.
Viu, Ricardo? Aqui um é totalmente diferente de um lado do outro, essa é a principal coisa que eu não falei. Sérgio, chequei o seu. Se pode estar não funciona aqui, eu vou tentar funcionar. Como é que é? Ficar usando aqui, eu acho que é mais fácil. Yes. How to have the full.
Oh wait, it's PDF. You can move either with arrows or with the mouse.
I think I'll do that.
Okay.
Okay. Mas eu posso usar aqui, posso usar tudo isso.
All right. Next presentation is by Sergio Fontes from the Observatorio Nacional on the Brazilian seismic network. Sergio.
Okay. Hello, good afternoon, everyone. Many thanks for the invitation, Retsky. Actually, I'll be presenting here one infrastructure that you built in Brazil, the Brazilian seismic network. You'll be talking also about some tomographic studies onshore and offshore. You are just planning some work, so I'll be presenting what you're planning. Well, the presentation outline is following the Brazilian seismic network. I'll take more time on that. Some scientific results you got from that, and offshore perspectives. Well, this is what you have now. We started this project thanks to Petrobras. Actually, it's composed of 4 subnets. It involved 4 institutions in Brazil: USP, UNB, UFRN, and Observatorio Nacional. It cost about 24 million reais, and this money lasts up to 2014, something like that. After that, thanks to Mariana, sorry about that, but thanks to Mariana, the CPRM, the Brazilian Geological Survey, started funding that, and so that's why you are still improving the network, adding some more stations, and putting all of them, most of them transmitting online, so you have it working okay these days. The things that are important, you have 86 broadband seismographic stations, and the data is public to Brazilians and everywhere. Well, anybody can use that. And I have a mission. The focus is on the Brazilian seismicity and to give support to R&D projects. These are the institutions involved: the Observatorio Nacional, the UFRN at the top, UNB, and USP, the guys involved in this coordinating it node. You have about 12 lecturers involved in this project, 16 technicians, 4 admin support, and a lot of students, undergrad, masters, PhD, and postdoc students right now. We're showing what was the steps that are required to install a seismographic station. You are showing the top there, the typical equipment Observatorio Nacional use, but it varies from each node. When you start, you select a place in a remote area in Brazil. You do some tests, initial tests, that are kind of power spectral analysis to show the quality of the data set. And normally what you have, the lower limit is instrumental, and the higher limit is based on an average of over 70 results from all over the world. So if your data set stays between these 2 limits, you can consider your site okay for installing a station. So there is some construction work in there, and I don't need to go through this, but a lot of work to get one station in working condition. You try to to have some thermal isolation to protect for temperature is a big problem on that. So we have also station in Trindade Island. You have a station in every place in Brazil, and Abrolhos also. So these are very hard to do to install some station like Tabatinga. If you see Tabatinga is very stream of Amazonia. So to get there was a big task for people there. The hardware, you have a portal at Observatório Nacional, and all the data that is received from our station is stored at Observatório Nacional. So this, and you keep updating this system. This overhead is kind of old. You have much more memory and everything right now. Also, what you use, you have a real time. You receive the data, and on a real time you are able to see what is going on around the world. So you get all the earthquakes that are happening everywhere in the world. You get it automatically, and you see what the magnitude automatically, the position, and then manually you check whether the data is right, if it's not some problem. The seismometer that you use and data logger use are different for each node. ONB, for instance, use a nanometric system. The Federal University of Rio Grande do Norte using RefTech. USP also use a nanometric. USP and UNB using the same systems, and Observatório Nacional using the Streckheisen STS2 and 2.5. Data transmission. Most of the stations from UNB is from satellites, just because the stations that are run by NB are in the northeast Brazil, and in the forest region mostly, and you then need a satellite communication. You don't have 3G signal normally. The UFRN uses 3G and satellite. You are now improving UFRN. Quite a few of their stations are still not online, but from the end of this year, all the stations will be online. You have money for that. You are already installing those. USP use a combination of satellite, 3G, and radio. ON is using 3G and satellite. This is a compilation of results for all stations you have. The noise level. So if you see the colors, you have the blue for, this is the USP, this is the ONB node, Rio Grande do Norte network, and the Observatório Nacional network. So you can see that, well, on average, everybody, all the stations are okay. You see that the stations in north are slightly more noisier because you don't have hard rocks over there. You have mostly sedimentary rocks, so the coupling is worse. You have more noise if our station is on top of sedimentary layers. No, I come back. So since 2010, you had a very, very low quantity of data stored, and this data set keep going up. And now in October 2018, you have 1 terabyte, just a bit more than 1 terabyte data set. This data is also shared with, you have a mirror at IRIS. IRIS is a United States incorporated research institution for seismology in the United States. So the mirror they have, and this data is also, well, most of the community gets the data from IRIS. And still is increasing every year. So you also have this portal that is updated regularly, where you have news, you have discuss about what is going on. You have several things on this portal, you have the catalog of the Brazilian seismograph catalog. You have a bulletin. You have all the stations. You can click on the station and get what is in there. You can retrieve the data from the site. You don't need to contact us. You can automatically get all the data you need for your research. This is if you look at one particular station, this is Cruzeiro do Sul in Acre. You see how the data set is being complete for most years. Now you are 17.1 just because the end hasn't finished yet. And you also have a kind of quality control of the average data set you have there. You've been appearing very much on the media this year. Over 125 reports in TV and printed and online in newspaper and radio. It's been important to communicate to population. Brazil is not a very seismic place, but you have some seismicity, and every now and then people get worried. So it's good that now you can tell what's going on. You can, within some minutes, to tell people the intensity of the event, the magnitude, why it happened, the depths, and all these things. Also in the press, and also you have quite a few outreach activities. For instance, you are in the Museu do Amanhã. If somebody is going to visit there, it is in a special room in the Museu do Amanhã, where they are monitoring the real-time parameters from the Earth planet. So you have our network is there. It's good for us. It's good to talk to the people. You've been presenting most of the National Week for Science Technology. You've been in the Geological Congress. You've been trying to communicate to people that you have this infrastructure. You also produce, who produced that is CPRM, the Brazilian Geological Survey. You produce a daily bulletin, and this is the 6th of November 2008. You just put in here because there was an event. There was a 3.2 event magnitude in the area where you went to do some work. So but the events in Brazil are normally very small magnitude. 3. Well, the last one that was over 4 was in 2016 in Maranhão, was it? So you don't have very big events. But you can have big events, and if that happens in areas populated, it can be a problem. Here you can show a kind of all the events that you had, both historical and events up to 2016. And if you see, most of them are under 660 kilometers depth, and very few deeper than that, relate to the subsidence of the Nazca Plate. The biggest events are this one in São Espírito Santo, and that one is Mato Grosso. Both happened in 1955. Now, one good thing about this network, if you see the number of events you had recorded between 2010 and 2012, when you were starting this infrastructure, you had about 69 events. Between 2014 and 2016, when you had most of our stations implemented, you detected 517 events, which is 7.5 more quantities. It doesn't mean that Brazil became more seismic. It's just because you raised our capacity of measuring it. No, I'm coming back. Also, if you see this year, you already have 487 events. Maybe there are a few more that you stopped this a month ago. Maybe you have over 500 events right now, which is good, and you're showing the events that happen in this period. Another thing that is important for our network is the azimuth coverage. If magnitude of the event is small, like magnitude 2, you can only see around yourself. So this station, if an event happens close to this station, for instance, only itself can measure it. But if you are considering larger magnitude events, so the coverage, the azimuthal coverage, so the smaller this is azimuthal gap, the more coverage you have. So for instance, with the network we have now, Brazil is prepared to see all event that has magnitude of about 4, no, magnitude of 4, not 4 kilometers, sorry. Okay. No, true. Well, with this infrastructure, you managed to have about 25 papers published. That was up to October. 40 presentations, scientific conference, 30 PhD thesis, master dissertation, undergraduate final project reports. This one study that's been done using this data set in Amazon Creighton. What you see there is a cross-section about 2 lines. The first one here on the top, the second one down at the bottom. You are talking about velocities, percentage of velocity. The blue means higher velocity, the red means lower velocity. So the Nazca plate is clearly a high velocity zone, and you can map it very clearly using this kind of studies, using tomographic studies. You're using data along the station that are distributed in the area. One more study that's been done recently was by Gotob et al., 2015. What you see here, the data set distribution is shown this map with the geology. Here you see the Rayleigh wave group velocity perturbations at different periods, 6 seconds, 10 seconds, 16 seconds, and 23 seconds. So the lower the period, the shallower is the information. And what you can see, the blue show the high velocity zones, the red the low velocity. You see that, well, the basin like Parnaíba and Marajó Basin and Paraná Basin are low velocity. You have the sediments that have low velocity. The craton, the San Francisco craton, the Amazonic craton, they are high velocity and they are showing in blue. And when you go deeper, for instance, we don't see much on the Parnaíba Basin here. You have less resolution, and also the Parnaíba Basin sedimentary cover is 3 kilometers, whereas the Paraná Basin is about 7 kilometers. And besides that, you also have a kind of high upper crust felsic that shows also low velocity in Paraná, according to other results. The results are here also showing what the resolution, the work you just showed now can tell you. The color show the spatial resolution. We have again here when you have red is the area where result you have more resolution. When you go towards the green, you have less resolution. It's mostly related to the density of stations in the area, and the ray traces are shown here. You have larger traces in the central area of the profile. That's always happen when you are doing seismic work or using tomography. The work now that you are planning in the offshore, you have now a project with Petrobras together with Federal University of Santa Catarina, and you'll be installing these six stations, OBS, ocean bottom seismograph, broadband seismograph down here. They will stay for at least 1 year, and the idea is to do similar work as you shown in the previous examples. And in this picture here, showing the trace that are possible. We are including Trindade Island data station plus the onshore onshore data sets that are from the Brazilian network and the stations that are offshore. This project can even be increased because we are now discussing with Petrobras to have a permanent network offshore. So maybe you have about 12 stations installed maybe next year sometime. It's always very slow. Well, you know all this problem. Thanks. That's all I want to show.
Thank you, Sergio. There's a question over here.
This is Bernd Adnoy. I think the problem about earthquake is very interesting, and the question is, has this any relevance for the oil industry? You know, we did something similar some years ago. We had a project with NORSAR, which is the Earthquake Institute, because we were trying to figure out what are the in situ stresses in the field, because that's important for oil production, you know, the wellbore stability and all that. So, we, like in Tampen in Norway, have most earthquakes in Northern Europe, about 100 a year. And by back analysis of all these earthquakes, we could support or the conclusion that we had a normal fault stress state in the Cretaceous, which you know, is the rock in question. And in Jurassic and deeper, of course, you have more tectonic events. But by back calculating the earthquake information, we could say something about the stresses in the rock. The only problem is that in our case, the earthquakes occurred from 12 to 30 kilometers, but yours are much deeper apparently. But there is a possibility to try to see if this information can be used for shallower you know, issues. So anyone interested can share some papers if anyone is interested in the subject. So, well, thank you very much.
Okay. Well, I think you can do some work that is worth for the oil industry. You are using broadband seismometers, so you have shallow information also. Can look at a focal mechanism, and in the sea, what is also interesting for Petrobras is to know the risk. You can know where they have infrastructure, where they are exploring oil, whether there is a chance of a big earthquake that may damage or may cause a very huge, how to say, big impact on the environment. There are quite a few things that can be done with seismology, certainly.
Just a small comment. The back calculation did not give the magnitude, but it would say whether you had a reverse fault, a strike slip, or a normal fault type earthquake. That was the information we got from the back calculation of the seismic information.
Yeah, you can do that, can't you? He's the specialist. You can do that. You can, that bow thing, you cannot.
All right.
Yeah. You can do.
I think I have to stop it here because we're on a real tight schedule. But Sergio, thank you very much. There's more to discuss after. The next two presentations will be given from Bergen. And so we have 1 or 2 minutes where we need to change the sharing of the screens. So bear with me for a second. I need the technician. Let's see. Can you help?
Let me see.
We have to stop sharing
He's
the
there?
screen.
Okay.
But he has to share his screen from his side.
Okay. He's there?
But we should stop sharing the screen.
Okay. First we need to have him.
But he is already there.
I don't know. Okay. Good. Is he there?
No. He was already connected.
Okay. Good. So
I see. Stop.
Stop.
You just go to the other one that you had and stop that one. That's okay. Okay. And there is not his Skype name. He's already online.
Okay. So I need to go to his screen.
Yeah, but he needs to do that.
Yeah, he needs to. No, I need to go to his screen.
Go ahead. Sorry.
And ask him to. Yes.
No, it's not that one.
It's team viewer. Share. Yeah. Okay. No, no. I think you need to.
It was that one.
Okay, accept this. Good.
Okay. Now,
I need to
are
share.
you able to provide technical help?
You just need to share the screen.
Share screen to you. No, but it's basically from
He needs
Norway
to do
to
that.
us. Okay, so that's his screen.
Okay, we need to stop sharing.
No, stop. No, what is seen from this camera? He should share the screen using this button here. Is it possible for him?
Yeah, I think so.
Yeah, there he
Yeah,
goes.
he's-
Yes,
Okay,
very good.
that's good.
Okay, it works.
Thank you.
Now we need to hear him. The next thing is we need to have the sound.
Can you hear us, Ritzka? He is listening us. Oh,
Yeah.
let me see.
It's supposed to be easy.
The microphone.
But he has to put his microphone on.
A câmera é esse aqui, né? Não, live cam é esse aqui. Alô? Alô, alô? A câmera. Ok, it's working. Não tá saindo o áudio aqui. Tá saindo. Okay.
Somebody's coming. We see him.
Yeah. Now you want to put in big screen there,
Yeah.
full screen. He needs to put in full screen. Maybe he has two.
He has two screens.
Can you hear us? He has two screen there. It's presenting another screen.
But we don't hear him.
Hello, Robbie. Speak again.
Okay, we are listening now.
Hello? Hello? Okay.
It's working.
Nice.
We just don't see your presentation. But it might be in the back here.
He's back.
Okay. Yes. Okay. I think you're on. I'm not sure if you have to use full screen, Stefan. Just go ahead.
How's
Yes,
that?
it works.
Excellent.
Okay, great. So, Ritzka, if at one point it cuts, just send us a text and I can we can start again. So thank you very much for the invitation to speak in this session. It's been really nice to listen to all the talks. I wish I were there in person. I think we both wish we were there in person. Unfortunately, heavy teaching schedules have prevented us from coming, but at least we can be there virtually with all of you. So today I'm going to talk about a project that I've been working on with my students here at the University of Bergen over the last few years. And the aim is to build a global database of receiver functions for imaging of crustal and upper mantle structure. You can see here all the people that have worked on this. And basically it's something that is not, well, I mean, it relates to some of the things that were discussed in the last a couple of talks in the sense that it's a method that was shown 2 talks ago, but that we tried to create in a fully automated way that can process automatically the type of data sets that we are collecting in Norway and that you are collecting in Brazil right now. So the type of seismic data that we're using is converted teleseismic waves, and some of you are very familiar with this and some of you aren't, so I'm going to try to explain very briefly what the theory is with those 2 figures here, one that's sort of more representing the model space and one representing the data space. So what we're interested in are waves that, teleseismic waves, so that is waves from distant earthquakes that illuminate a region from below, and this is basically a profile through the earth, a vertical profile through the earth. You have your surface here, it's the straight black line, and you have some discontinuities in material properties in the subsurface, like here a perturbation in S velocity and in density. And let's say you have a seismic wave, a P wave that comes and is incident upon the discontinuity like this. Part of the energy will continue towards the surface as a P wave, part of it will be converted as an S wave, which will then travel at a slower wave speed towards the surface and be recorded at the stations that are here. And what you're recording at the stations is the data, seismic data that you see there. So you have your P wave that arrives first, and if there were nothing in the subsurface, well, this could be quite quiet after the P wave, but what you see here is a bunch of wiggles that correspond to the conversions that are occurring from this P wave at discontinuities there in the subsurface. So to try to generate an image from this, what we do is we separate the incident wave field from the converted wave field, just basically geometrically at the surface. We deconvolve the signal that contains most of the converted wave field. We deconvolve the incident wave field from the converted wave field, and we obtain a signal that kind of looks a bit like this, and that's called a receiver function, which again was discussed a couple of talks ago. And the way to image with a receiver function is you take this type of signal, once you've done the deconvolution magic and things like this, you rotate it about itself like this, and you change the time scale into a depth scale, assuming that you have some information about the sort of overall, say, 1D velocity structure that you have in this region. And then once you do this, you have what's called a receiver function, and you can start imaging the subsurface with this. It gives you, as you see here, information like the P wave will tell you where the surface is, and the discontinuities, the different pulses corresponding to these converted waves indicate where the discontinuities are as a function of depth. So you can already use this as a simple tool to image the Earth. But you can also use this also as a building block for more sophisticated methods that can give you information like profiles or 3D volumes of discontinuities through the Earth, which is what I'm going to discuss during this talk. So despite being disarmingly simple, the receiver function method still requires quite a lot of user input. And this is why when people do receiver function, they tend to do them locally or regionally at at arrays of broadband stations that are recorded at the surface. This here is an example of a few experiments. I just want to start with this one, which is kind of interesting because this is the site of the Norsa array in Norway, where Lev Vinnik, who's a pioneer in receiver function studies, did what some consider to be the first ever true receiver function study in the 1970s, in which he imaged the lithosphere and the mantle transition zone below Norway with data that at the time was some of the best data to do some of these types of studies. So really, original receiver function was done there. And when I did my PhD and postdoc and the research that I've done in the last few years, I've worked on small arrays over here in Alaska, this one in Cascadia here, so in Oregon. And when I was doing my postdoc, we wrote like 2 or 3 papers just based on one station here in Massachusetts. But of course, there's a lot more data than this that's available around the Earth. And this is as of 2013. This was all the data that was publicly available that one could collect from the IRIS archive of data in the U.S., including, as you can see here, a lot of stations from Brazil here. And the idea of the project that we had was to basically use all of those data to produce receiver functions globally that could help obtain some images at global scale without being impeded by geopolitical boundaries, if you wish. And with the idea that if we were able to do some receiver functions consistently across all of these stations, we'd be able to get better information about how structures in the crust and in the upper mantle vary globally. So as part of this project called Glimmer, with students here, we developed an automated method that basically can download data from all of these stations and compute the receiver functions automatically using sort of some of the state-of-the-art tools that we have developed over the years to measure quality control, to do quality control, and to do optimal deconvolution with these data. So we've done this, and here's Glimmer. So the database right now in numbers. So we have basically the number of stations that you saw in the previous image is slightly more than 8,000 stations that have recorded over the last 30 years a total of about 10,000 events, and that have generated 2,600,000 receiver functions, and these are both radial and transverse receiver functions. And what we've done is we've created a series of tools that we plan to distribute to the general public, I mean to the scientific public, but also to make publicly available so that people can use these to look at receiver functions everywhere. Now, what you can do with receiver functions really depends on the density of stations that you have. And I'm going to try to go a bit more quickly here because I see that it's already 5:45 here, Bergen time. Okay, so the type of methods that you can use really depend on the coverage that you can get with your receiver function. And this is what I called here the receiver function aperture. That's the sort of area that a receiver function can cover beneath one station, right? So you can see that it goes from 20 kilometers diameter here at the MOHO depth to almost 600 kilometers at the 660 discontinuity. If your stations are separated such that those sort of apertures don't overlap at the depth that you're interested in, then you have to look at individual stations one at a time, and you can look in terms of back azimuth, etc. But what you mainly get is a 1D image below each stations. However, if your stations are very dense, you can have overlap of these aperture, and you can start to do some more sophisticated methods, get some volumes, do some migration, do some common conversion point. And I'm going to show some of these tools that we have developed within Glimmer. So the first tool that I'm going to show, which is a tool that's available right now to everyone online on the Glimmer website, is a sort of Google interface, a Google map interface like the one that you see here, where you have all the stations indicated. You can zoom onto anything, pick any station by just clicking on it with your mouse, and you would get here, this is for a station in the eastern US, in Massachusetts, you would get the receiver function at that station, where you can see the receiver functions mapped to depth, so 0 to 200 kilometers. That's the stacked receiver function. And if you click on some of these other buttons here, you would get more information about this same station with, again, the stacked receiver functions from the surface to 200 kilometers depth, from the surface to 800 kilometers depth. And here you can see the individual receiver functions here that contribute to to these stacks that you have there, both as a function of ray parameter and as a function of back azimuth. But here you can see clearly, for example, for Massachusetts, you can see the MOHO, the mid-lithospheric discontinuity, the lithosphere-asthenosphere boundary, When you look from 0 to 800, you can see the 410 and the 660 discontinuities there. So that's a tool that exists right now. If you go to, if you have dense arrays of stations, then you do more sophisticated approaches, I was saying. Here I'm going to show you one of the things that we've done last year is create a global grid of common conversion points called CCPs. And what we do in these is we basically combine conversions that are recorded at different stations that would convert at similar points at depth, and we stack them together to produce some virtual receiver functions that show the conversions that happen at bins and depths, right? So it's basically a similar method to CMP gathers in reflection seismics, for those of you who know, but using teleseismic waves. So I will skip this quickly here to just show you a little bit what we've done. We've created this global grid of CCPs that you can see there. This is a 5 degree by 5 degree, but we can go down to 1 degree or even like half a degree by half a degree. Here is just so that you can see how it is. And for each of these grid points like this, we go at different depths and look at all the receiver functions that could convert at these depths, stack them, then create volumes of receiver functions, of volumes of image for all of these regions. This is in practice where we compute these CCPs. So again, you can see the stations there as the black triangles. The red dots indicate where we actually compute the CCPs, because although we have a global grid, we don't have to calculate them everywhere. There's a lot of areas in oceans where we don't have stations, so we don't compute them there. And so I'm going to show you examples of these CCP stacks that we've computed for North America here, below US array, and for Eastern Eurasia. So let's go back here. Let's say you pick here a box around North America. So we've made this tool, a MATLAB-based tool, where you can basically then get images that allow you to explore, or a tool that allows you to explore these images in 3 dimensions. So here we're going to look at an image that is along this line here and along that line that you don't see very well, but that's north-south here. And this is a little movie that shows you the tools that we can use to investigate these receiver function profiles. We're going from 0 to 800 kilometers depth, and we're crossing the entire US here. You can change the scale to enhance the colors. You can move this in 3 dimensions. And here, what we can see is the moho here at the top in 3 dimensions, and the 410 and 660 kilometer discontinuities. And now we're moving along this profile from the center of the US to the north of the US, and we can see how the 410 and the 660 sort of vary as a function of latitude below the US. And basically you can take any regions around the Earth, move these volumes around and get images like this that would give you information about structures in the subsurface. I'm going to skip this slide here because I see that we're running out a bit of time. I mean, you've noticed in the previous image that I showed you that the profiles that we have are perfectly east-west and north-south. One of the most recent modification that we did to this code is that we added another little cursor that allows you to now look at oblique profiles. And this is an example going from the Himalaya into the North China Craton, again, where you can see the 410 and the 660. So now there's the possibility of not just having east-west, north-south profile, but also having oblique ones. And to finish here, I just want to show you that also, I mean, you can look at volumes, but if you want to do more, say, surgical analysis, if you wish, you can also take these CCP grids like this and pick points to make some specific profiles across any region that you want. And here is a profile that goes from Cape Town all the way into the FR, and that gives you, again, 2 images, one from the surface to 250 kilometers, one from the surface to 800 kilometers. And with the interpretation, you can see that you can see the moho over 6,000 kilometers here, and very nice variation with respect to the different geological environment that you're crossing. And And over here in this lower one, you can see how the mantle transition zone, its thickness varies as a function of where you are, with a noticeable thinning when you arrive at BFR, which is what you would expect. So to finish, here's a final image. This is what we've done in Glimmer, and what's next? Well, the idea is to continue expanding the database at this stage and add and process data from other sources, Orpheus and national networks. So, again, Sergio just presented all the data from Brazil before that seems to be public, so it's something that we could add into this database. Also adding S2P receiver functions in addition to the P2S receiver function that I showed. The idea is to bring Glimmer completely online via the EPOS website here in Norway, and to continue developing more advanced imaging methods to obtain high-resolution profiles through methods like this. And just if I have 1 minute, one short minute here, the examples that I've shown you are examples that I've shown in these talks before. So they were for example, for the Eastern U.S. But I'm directly online right now, going through this this Google interface that we have. So you can see the website is a bit of a complicated website, but the link is on a paper that we wrote recently. But I can go here over some of the data that is in Brazil, and I can go and pick, these are the stations that were available from IRIS at the time when we started the database. And you can go anywhere and pick on stations and get, like this, for example, the receiver function for below Brasilia, where you get a nice MOHO at 40 kilometers. And if you go in one of these things that I was showing before, one of these little links, you can again see that we have, this was created with more than 100 receiver functions. You can see again the stack here to 200 kilometers with the MOHO here. In the deeper one, you can see a nice 660 discontinued at 660 kilometers, maybe not quite as clear in 400. And we can just go and look at many other stations like this, but I will spare you. This is another very good one, for example, in an area that I'm afraid I don't know exactly where it is, but maybe some of you do know. And this is the link to the paper that you can go in that would give you the link to this web interface. So I'm going to stop here, and thank you very much for your attention.
Thanks a lot, Stefan. That was a really nice presentation. Are there any questions from the audience here in Rio? I have one question myself. I mean, one of the clear things that you see on this global distribution of stations is that the coverage in the oceans, of course, is very, very low, because there are basically fewer stations there. So what would it take? I mean, how long do you have to leave a station on the ocean bottom? Is it half a year, or shorter? I see also here in the audience several people that maybe have an answer. But how long would you have to have a station offshore to actually also get more data coverage in the offshore?
Well, okay, so that's a good question. I mean, I guess the first way to answer this is, how long ideally would you need a station in general, on land or offshore, to get a really good receiver function that stacks well? And I would say that you start to get some good stacked receiver functions and some good images at around 6 months. But ideally, to really get a nice coverage in terms of both back azimuth, but also epicentral distance that gives you a good stack, and that of course depends on the area of the world that you are trying to look at. So that is how much global earthquake coverage you have. I would say more 2 to 2.5 years would be ideal for a land station. So for an OBS, for an ocean bottom station, I would say about the same, right? Ideally, you would want 2 to 3 years or something like this to have a really nice data coverage. But of course, the problem with the ocean stations is that they tend to be a lot noisier, and there's a notorious problem with the ocean station that makes it quite difficult to compute receiver functions. But one of them is the noise. So the noise is much higher than stations on land. And the other one is the multiples that are produced by the water column, which tend to interfere with the conversions from the MOHO, etc. So there's a lot more processing that goes into trying to extract or remove the multiples that you can get to the MOHO. And that's quite complicated. There's a few methods that exist out there, but you never get images that are quite as clear as the ones on land. So there's some work to do there as well.
All right, Stefan, thank you very much. Very nice presentation. We'll continue with the presentation from Bergen by Rob Gawthorpe with a quite different focus, sediment-free basin evolution and subsurface analogs. Rob, the floor is yours.
Okay, as Richard said, this is a bit different focus. I want to look at some examples of using outcrop analogues for getting information on sedimentary basin fill with applications to oil and gas exploration and production. And the example I'll show is some work that we've been doing as part of a Norwegian Research Council Petromax 2 project on the Corinth Rift, which ties into subsurface studies along the Norwegian continental just to home you in on the subsurface part, trying to address. This is a view from part of the northern North Sea. We're looking at a synrift, intra-synrift horizon picked from high-quality broadband seismic data. And in the purples to yellow, red colours is a time thickness map down from an unconformity within synrift units. And in the lower part of this figure is a blended attribute map that tries to image some of the seismic geomorphology on the horizon. And so what you can see here is some normal faults, which have quite complex geometries, and throw variations, which are fairly typical, along major border faults and intrabasin faults. There's another fault here with a number of splays. And the warm colours, the yellow and reds here, pick out erosional features, which have this dendritic headward areas, and they're supplying or funneling sediments across this faulted topography into the basin, and the bright colours in this blended attribute map are picking out some deep water turbidite sand-prone units. So this is, with a lot of work, the type of image that you can get to try and highlight a source sink analysis of a rift basin, trying to target deep water rift axis depositional systems. But as you can see, even from this very recent data, the actual quality of information you get from the seismic geomorphology is quite limited on these depositional systems. So this is where understanding systems from looking at a modern rift setting and using outcrop analogues comes in. So why go to Corinth? Well, Corinth is an active rift, and it's probably one of the most data-rich active rifts in the world. So because it's active, we have seismological and geodetic constraints on the structure and on the extension rates. It's a closed system, as illustrated by this top image. Here we have this Skinos fault was last active with a magnitude 6.5 earthquake in 1981, and we're looking at the hanging wall epicenter, the Gulf of Archinides here, and it's in the hanging wall of the fault. And so this is, you can see the erosion area and footwall. We have sediment transport down these alluvial fans and fell deltas into the sink, the basin area. So we can attempt to constrain all of that system in these types of analogues, where we have the hinterland drainages present and preserved, which is quite common in many ancient rifts. Also in Corinth, there was a northward migration of rifting about 2 million years ago, where the rift shifted 30 kilometers north. And that allowed uplift of the earlier rift fill. So this middle image here shows 600 meter high, so seismic scale exposure of hanging wall deltas. And here's the border fault that was active at that time. So we can go from effectively rift scale to seismic scale to outcrop scale in the rift. And then last year in October to December, there was IODP Expedition 381, which drilled the current Gulf with over 1,700 meters of core, which is tied to a dense network of 2D seismic data, allowing us to look at the very recent rift history in high resolution and and tie that to well-constrained climate and sea level records. So, as I mentioned, this provides quite a unique data set for looking at rift basins, both from a fundamental science point of view, looking at early rift evolution and the controls on basin fill, but also then using that data set to apply to exploration and reservoir characterization studies. Okay, so let's have a quick look at the Gulf of Corinth. Set the scene for, I'll show you modern depositional systems and then zoom in and look at some of the older outcrop analogues that we're working on. So here's the view Corinth Rift. It's about 100 kilometers long. It's about 30 or so kilometers wide. The colors here, green is pre-rift Helenide thrust base, effectively a basement to the rift. Yellow are Pleistocene synrift sediments. Topography is highest in the west here. It gets up to nearly 2,400 meters. And in the modern Gulf, the basin floor in the central part of the Gulf here gets down to minus 800 meters below present day sea level. The red faults are the faults that have been active over about the last 700,000 years, and the black lines represent faults that were active in the older parts, going back to about 5 million years ago. So cross-section through the rift in the western part here, going from south here, to north on the right, shows a sort of typical profile of a series of tilted fault blocks. The Medon Gulf is the blue colour here. So it's fairly typical in terms of the fault block size and the throw on these faults of many rifted margins. I mentioned that the catchments, they're still there today, so you can do quite a lot of work looking at the sediment, erosion and sediment flux into the rift. So this is a map based on forward modelling the last 300,000 years of drainage and sediment supply. So the warm colours are high sediment flux into the rift from the catchments, and they going down to yellow, which are lower sediment supply from catchments, and the darker green colours are the thickness of the sediment during that last 130,000 years. So one thing you see from this is that the western part of the rift, where the topography, these dark grey colours in the background, high topography, in the west is the main source of sediment, yet the main depocentre is in this central part of the rift. So the implication of that is that there's quite a lot of a long strike transport over many tens of kilometres from the source area to where the ultimate sink is of the sediment. That's one of the targets on the IODP is to evaluate the sedimentation rates around the Gulf by tying that to the cores. This is a view then looking at that westward end of the rift. We're looking southwards. This east and west are Haliki faults are the currently active faults. There were earthquakes on those in the 1990s. And we're seeing the hinterland to the south of the active faults just a few kilometres inland, getting up to over 1,700 metres. Here in the blue colours are the subaqueous part of the rift down to minus 800 metres. And in the hanging wall of the active faults we have where these high sediment supply is from those large catchments. We have a series of hanging wall deltas with clear delta top, shelf and slope, and these pass downward into a series of transverse submarine canyons which link into an axial fault control canyon that then transports that sediment eastward into where those main epicenters were. So keep this in mind. So we've got transverse entry points supplying sediment to the rift, but then along the rift axis, quite marked along strike transport of sediment. And in this case, it's to the east to the ultimate epicenter. So the outcrop analogue that I want to show you is a similar setting. So this is now going back to paleogeography for the rift between 3 to 2.5 million years ago. This is, we were just looking at this western area. We're now going to move to the east a little bit. And the brown colours here are fluvial sediments. The blue colours are lacustrine, deep lacustrine deposits, with these flesh-coloured units being a representation of some turbidite deposition systems within this overall deep lake. And the system that we're going to look at is sourced from this drainage system through this delta called the Mavro delta. And then, like I just showed on the modern bathymetry, the sediment comes in transverse to the rift and then flows axially into this submarine channel and fan system off to the east. And I'm going to be showing you the present-day geology around this area, and then we'll look at some of the sediments around this amphitheatre fault and the submarine deposits in its hanging. So now we're looking at the present-day geology superimposed on a Google Earth image. So we're looking to the southwest. Here's the border fault that was active during that early rift phase. The yellow colours are effectively deep lacustrine sediments. I've highlighted some of the main fault zones, with the green and grey being pre-rift rocks. And the brown units here are a series of deltas, which mark quite a long-lived sediment entry point. And we'll be focusing in on sediments which at the shoreline created the Mavro Delta and then bypassed and were funneled along the hanging wall of this amphitheatre fault to the east over 20 kilometres to where we'll be looking at them in the hanging wall of the amphitheatre fault near this village of Risa. The next view is from the footwall of the amphitheatre fault, looking at those exposures of those deep lacustrine turbidite deposits. So this is the view from the footwall. So you're stood effectively on the fault zone of the amphitheatre fault, and you're looking into the hanging wall epicenter. So this was from cliniform heights of the delta in several hundred metres of water at the time that these sediments were deposited. And to give you an idea of scale, the cliff section here is about 200 metres, and we're looking obliquely along this cliff profile into the distance here is about 7.5 kilometres. So we've done a whole series of traditional structural and sedimentary sequence stratigraphic work on here, plus digital outcrop works to characterise these sediments. So some of the units that we've recognised in blue here are a major series of stacked turbidite channel complexes, and we'll be looking at those in a minute. And then also focus on this much more sheet-like yellow unit, which is a series of submarine channelized fan lobes. So here's a stratigraphy from that unit. As you can see here, it's quite muddy overall. there's this local development of in blue unit here, a series of channelized and vertically stacked submarine channels, and then this more sheet-like unit sands and muds. So cross-section going from the amphitheatre fault, where we're stood, into the hanging wall, shows you in blue colours here the geometry of this submarine channel complex. So you can see it's quite localised in the immediate hanging wall of the amphitheatre fault. So there's a fairway which is of the order of just over 1 kilometre wide. It stacks up at over 200 metres. That's flowing axially in the hanging wall of this fault zone, giving us quite an impressive series of stacked turbidite deposits. And here you can see some of these channelized bases to the flows, but just basically a vertical stack of submarine channels that form a belt that's about 1 kilometre wide. So this is, we'll just go back for a second. So if we now focus in on this more sheet-like unit that we can track over these outcrops, this is a drone video of that unit. So this is the unit 13 that I'm talking about. It's about 30 meters thick. So if we just run this, it will give you a nice view of some of the features of this sheet-like body. So you can see it's quite variably internally. There are some quite sheet-like turbidite sands, but then as we swing round here, also some quite winged-like channels, several horizons in here that look like they compensationally stack, so they're offset from one another. And then as you come down at the bottom here, a very high net to gross sand package with very laterally extensive, but again locally channelized units. And then above that, we go back into a largely fine-grained succession, this white colour here, and below also into a quite fine-grained succession. So what controls that? Why are these fan lobes, channelized fan lobes, in this part of the strip? So we've been trying to look at that from a number of ways, and this is a plot of the palynology going through that interval. So I've highlighted the sand-rich interval here, and without going into any great detail, but you can see that there are quite distinct differences from the mudstone units above and below that sand-rich unit compared to the sand-rich unit itself. So the sand-rich unit tends to lose forested palynomorphs, but then has an increase in steppic and herbaceous elements. And that's quite similar to what you see in quite recent glacial-eustatic cycles. So what we think is happening here is that these marl-dominated intervals that are quite fine-grained have widespread forest cover with a well-developed root system which stabilizes soil and reduces erodibility in the catchments. And so you actually transfer only fine-grained hemipelagic sediment dominantly to the basin centre, and that's characteristic of interglacial times. You go up into the Unit 13 where we've seen those channelized lobes. The vegetation changes to a much drier shrubland and steppe vegetation, where we have increased soil and sediment erosion. So we have a large supply of coarser grain size fractions to the basin, giving us our turbidites, and then going up into the overlying unit in another interglacial, we go back into the forested cover, which again traps a lot of the sediment in the catchments. So what the implications of some of this study and how are we linking this to, say, the North Sea, is that on a regional scale, it allows us to address that catchment to basin routing system. So in terms of important take-home points are pre-existing topography and the antecedent drainage has a long-term impact on the sediment routing in rifts. It's not just about the rift topography itself. That there's this offset often between where the main entry points are to the rift and where the axial depositional centers are. And they're often offset by several tens of kilometers. So from an exploration point of view, you need to take that regional perspective into account. And then from these examples where we've got detailed multi-proxy studies, as well as sea level, vegetation and climate can have a big impact on when you actually deliver the potential reservoir or when you develop regional seals in the basin field. And then on a more production reservoir scale, we've seen stacking of high net to gross reservoirs in the hanging wall faults. The facies belts have a tendency to elongate parallel structure, but also have structurally controlled pinch ends. And then the type of data sets that we develop have a very rich source of geostatistical information for sediment body geometries and also for providing training images for reservoir modeling. Thank you.
Thanks a lot, Rob. Very nice presentation. Any questions? No. If not, we'll move on to the next presentation by Ricardo Trindade. We'll have to stop sharing screen with Bergen and from your side, and we have to share again from our side. So I think I may need some technical support here.
I should call again? We close the conversation. I need to call again?
Not that one. No, it's not him. It should be. No, it's his.
Yeah, I know, but maybe it's open there. Because the two accounts is.
Yeah, but that is the wrong one because he has.
It's a very strange account. It has lots of letters and numbers.
Is he still online?
No, he's online. Yeah.
He's still connected, so we just have to share our screen with him.
But I can't. I need to start a conversation with him, with the conversation. Or the only way is to start a conversation, and then, okay, this we send our screen. Let him. No, you stop. You should start. Yes.
You mean he has to connect to us?
No. Yeah, he wants to share. Yeah. But when the communication. Yeah, now.
Yeah, now I can share.
Okay. That's good. Now we are transmitting our screen.
Okay.
Watch the presentation.
I can find it. Okay.
Now we need just to
but
block his sound.
I think he stopped the. Let me see before he starts. Need to start again.
This one?
Not this one. When you start the communication, click here, share the screen.
Success.
We are now transmitting our screen to him. Okay.
Let's just take this.
Yes. Okay. It's okay.
Rob, can you hear me? Yes, hope so.
Yeah, we can hear you, Ritzka, and I think you're just trying to share. Yeah, got your screen as well.
Good.
If he's seeing our screen, you are seeing the screen here?
Yeah, we've got, can see the screen and we can hear you.
Okay.
Ricardo. Trinidad from USP. I'll just let you introduce your title yourself.
Okay.
Ricardo.
Thank you. So I'd like to thank Ritsky for the invitation. Okay. Okay. And I'm going to talk a little bit about a project we are working together. It's called Stream. And the intention is to couple observations in the continent and observations in the offshore and onshore using geophysics and also geology, and couple that to understand better the margins of the South Atlantic. So the point of the talk is I'm going to talk about a little bit about the South Atlantic margin, some problems we have, potential old analogs in the continent. That's a way to inquire the deep structure of the continent, of the margin. Then the need we have for deep geophysical data, because we have a few of those, that some of them have been shown here by some colleagues, Suarez and Ingen. And also to talk a little bit about the Stream project. So we are in this context of this margin. The idea is to understand or to focus on this southeastern margin here, where the margin of the Atlantic does a bend from Espírito Santo's north-south to Rio and then Santos Basin. Looking at the Angola margin and also the equivalent in Brazil, we have contrasting interpretations of the distal margin particularly. Some colleagues call for a mantle exhumation in this sector, some suggest a highly stretched crust, some suggest a magmatic addition. And to understand better this, we need to have better results for geophysics, some geophysics that provides compositional information, but we can also inquire the rocks that are deep-seated in a continental South America, also by looking at the rocks when they crop out. So I'll show something that can be an old analog for the extreme case of a mantle exhumation. We are going to see also the geophysical image of that. And then we are going to see what we have as a geophysical result for the margin and what we want to do to advance knowledge in this subject. So first I'll show what would be a old analog of those of that mantle exhumation. And we think that those ultramafic bodies that crop out along the Araguaia belt are what we would expect of an extra hyperextended margin, an ancient hyperextended margin that has been afterwards compressed. So what we see is the exhumed mantle stretched and then compressed again to form the Araguaia belt. We have those ultramafic bodies. The Quatipuru is the most known one, but we have also Serra do Tapa and other Serra do Tapa and Quatipuru are the biggest ones we have studied in this region. This region is exactly in the middle of the South American continent. Here's in the middle of Brazil, between the states of Pará, Tocantins, and Mato Grosso. So that's the outcrop conditions. It doesn't look like, but they crop out very nicely. We have some host rocks that are very low-grade metamorphic rocks. Those are the host rocks to those ultramafic complexes. Those are the phyllites of the Couto Magalhães Formation. They are very weakly metamorphosed. We can see sedimentary structures in those. And within those host rocks, we have two large outcrops of ultramafic rocks, but also are capped sometimes by basaltic and pilolava basalts. And in Serra do Tapa, we have some drill cores that cross the whole sequence, and we can see the basal contact of the ultramafic succession. Here we have the Habsburgites. Then we have this serpentinized Habsburgites, and then we have some silexites and talc zones going to the serpentinite at the most altered zone. That's interesting that the contact is very rich in silica and has some indication of some shearing along the the basal contact of the Serra do Tapa, similar to what people see in the Alps in some equivalent sequences. In Quatipuru, we have inside the Habsburgite succession some donitic veins and evidence for late melts that were formed in those successions. And we interpret those successions as part of a mantle that was exhumed, in part because they are very, very poor in the equivalence of volcanics in the region. And we have for this region also some deep geophysics. So we have here the paper by Daly in 2015, together with the colleague Suarez. That's a seismic reflection. And it shows here the zone we were studying surface. It roots into this major suture that is marked by a completely different reflection pattern in deep in the crust and going to the moho. Here we have a detail of that section that was interpreted here as a major suture that was called the Quatipuru suture. Here the youngest basin, and here is the border of the Parnaíba Basin. That's a major basin to the east. This region has been also investigated using refraction seismics. The important thing about refraction seismics is that it shows not only or not mainly the general structure, but the density or velocity profiles across the region. So what we see is there is a contrast between this western part that's considered to be the base of the Araguaia fold belt. Here is the same structure that was shown before. And here you see that the basement beneath the Parnaíba Basin is completely different in terms of density structure than this western part. Also confirming that we have different blocks that were amalgamated that are now hidden beneath the Parnaíba Basin. This is a very recent paper by Suarez that's here in the audience, showing also there is a difference in the profiles between the Grajaú block that's in the middle and what's the Amazon Craton to the west. In the case of the South Atlantic, as has been shown before in the first talk of this afternoon, we have different possibilities of interpretation of the nature of the deep structure, either in the African margin or in the Brazilian margin. And this, in part, we can have a very nice image of the structures inside the crust in those two sectors related to high quality reflection data that we have. But we have very little constraints on the crustal structure due to given large uncertainties in nature of the mid-distal margin. And because of that, we have all those problems in interpretation. And also, this has a very strong implication on the thermal history of the basin field. And this has strong consequences for the oil industry. So we need much more refraction studies, and also integrate those studies with other geophysical results and also with forward modeling. And that's the approach we want to use in the STREAM project. So here is only to repeat and show again the Samba lines. We have two main lines and a third line that was done by the French group in 2010-2011. The papers were published in 2015. And they show there are at least 4 large domains along the margin. The crust that was not stretched. Then they have the neck necking zone, then a zone with crust that's very thin, and then this zone that was interpreted in different ways depending on the paper that they published. Some it can be eventually the preferred interpretation is that this is related to a anomalous crustal oceanic crust. But the word anomalous says a lot about the result. The interpretation they have, they proposed based on refraction seismic is consistent with the results they have from gravity data, and that's interesting. And that's something we want to do is to couple the refraction seismic acquisition to gravity and other geophysical results. And here is the compilation of the two lines showing the lateral variation that is interpreted based on the results they obtained. And so in the case of our project, the STREAM project, it puts together people from UERJ, that's State University of Rio, USP, São Paulo University, National Observatory. If Soares comes in, we are going to have people from Brasilia as well. And Ritzke Huismans, Rob Galtorp, Håkon Fossen, people from Bergen, and also colleagues from Oslo. And the idea is to put all those geologists and geophysics together to try to better understand the structure, the deep structure of the margin. So this has started already about 5 years ago with the collaborative research that is being done between State University of Rio, São Paulo University, Bergen, and Oslo already. So the idea is that now São Paulo University has a oceanographic vessel that is fully is available for this kind of work. So we can have we can produce at the university offshore refraction data, and then we are going to use the infrastructure that is available to us to buy some new infrastructure and have the help of the UIB and UIO expertise on the refraction data acquisition. The idea is to constrain offshore crustal structure, thickness and nature of the transitional domain in these deep water distal margins, and integrate refraction and reflection data. We have some broadband results to constrain the links between basin fill and rift evolution. And then with those results, we can constrain better the numerical models that are going to be produced also in the framework of the same project. The idea is to, here is the location of the profiles we want to do. Those are the profiles A, B, C, and D. We are going to start with the A and D. Here we have the onshore portion of the study that will involve geology and geophysics. And here we're going to have refraction seismics together with gravity and magnetometer, and also magnetotellurics. And then those results are going to be incorporated in forward modeling for rift margin evolution to understand and to better constrain this the evolution of the margins. And the idea is that we are going to use those results to test the geodynamic models we have along the South Atlantic, use the geophysical data to constrain the numerical models we are going to build. And this stream is also a very nice opportunity for capacity building in Brazil. And in that way, it's very adequate to this talk, because in fact this is a clear case in which Brazilians and Norwegians are going to work together to better improve knowledge in the margin of the Brazilian marginal basins. And that's it. So, thank you.
Thank you, Ricardo. Any questions for
Ricardo already showed a lot, which is very good. So let's just get this up. All right, so what I will do in the next 5 to 10 minutes or so is to just give you a brief motivation for why the type of problems and the type of open questions in the margin of the South Atlantic, and how we have used forward models to try to address them. This result of many different pieces of work, including a number of people that I'm not listing here, but there's certainly a number of co-workers involved. So I'll show you briefly two highly contrasting interpretations of the same margin segment that illustrate how difficult it is to actually interpret these data, and they also illustrate the need for additional data, refraction data, as also Ricardo mentioned. I'll show you a few forward models that we used to study margin formation. I may skip what I've on 3D rift segment linkage in Santos. And so here's one interpretation by Patrick Contenier and co-workers from Total, and they have basically a seismic section, reflects the seismic section from INGEO, long offset data. This type of data have in a way revolutionized the way we look at margins, because there's a lot more information that we can get out of them. But what you can also see is that in these very long profiles, there's still areas where it's quite difficult to interpret. So we clearly see the base of the crust, the moho. At some point we lose information here. We see salt deformation in the top. And these authors, they have used this interpretation in the framework of a mantle exhumation model. And so in this case, they have an interpretation where they have basically a crustal section that's necking in the distal margin. They interpret exhumation of this green material to basically the seafloor mantle exhumation before the start of mature oceanic crust formation. Now, I should note that there's basically very little constraints in the seismic image here on what's exactly happening over here. It could be mantle exhumation, but it could also be highly extended crust, or it could be magmatic addition. Here is another more recent example, a little bit further north, but it's essentially the same margin segment. And here they basically have a very different style of extension of this margin here. Very distributed, very large offset, normal faults that are essentially flat, with exhumation of the lower crust to the base of the sediments. And so quite different from the previous picture. And this illustrates some of the difficulties in interpreting these margins with reflection data. A few examples of what we've learned from thermomechanical models and using computational fluid dynamic models on a very large scale that allow us to do computational experiments where we compute how the crust and lithosphere and also the mantle below deform given certain boundary conditions and specifying material parameters. And so we typically extend the continental lithosphere here on top of a large mantle domain. So this is a very large domain, it's 600 kilometers deep. We have the continental crust and the mantle lithosphere, and we can vary parameters inside this domain to see how they affect the style of passive margin formation. So one of the things that we have found was that the rheology of the crust, the strength of the crust, is very important in controlling the style of deformation. And so here I have basically sections of the strength versus depth for the crust and the mantle lithosphere for different types. So we have very strong cases and contrast that with very weak cases. And this gives very different response when we basically start deforming this. And so here just three different examples. In the top case, which is basically a zoom up from the central part of this model domain, after about 100 20 kilometer of extension, we see that the continental crust, the mantle sphere, are broken up, and here we have a basically passive margin with basically a oceanic spreading system, if you wish. The yellow material is the mantle below the lithosphere that's now at the surface, and at this stage we would expect mid-oceanic ridge spreading system. If we weaken the crust significantly, then we can see that we have very different ridge style. We see distributed extension in the top layer, and the lower part here is rupturing very efficiently. And so this is just a consequence of varying one parameter, the strength of the crust. Now we've compared these different types of models with natural systems, and here is a reconstruction for another example, Iberia and Newfoundland, which is the type example of a system that ruptures in a very narrow fashion. We see here that continental crustal sections are thinning from the reference thickness to zero of about 50 kilometers, and they exhume mantle. And here on the right we have the evolution of a forward numerical model that shows very similar behavior. Very strong crust resulting in these very narrow margins. Now this does not reproduce what we observe in the South Atlantic, basically the conjugates between Brazil and West Africa. And so here in the South Atlantic, and this figure was shown by Ricardo already, we have a lot of high quality reflection data and they image basin fill, but we have insufficient constraints on crustal structure, and there are large uncertainties on the nature of the crust in the mid and the distal margin, and this has implications also for thermal history and basin fill, which is why it has relevance for exploration. And so there's a need for combined reflection and refraction seismic data integrated with forward modeling, as also said by Ricardo, and one of the aims of the collaborative project we're setting up. So here is a typical model now for that we believe matches some of the observations in the South Atlantic. This now is basically an animation with again the crust and mantle sphere, where the crust is very weak, and we can see if we run this forward, we essentially see how these systems evolve in time. We see that the mantle sphere here below ruptures very efficiently, while the crust is extending in a very distributed wide rift mode. And after a significant amount of extension, we see actually that we start forming sedimentary basins on top, the gray material here. Extension localizes here, finally in the distal margin where it will break up, and it produces extremely wide rifted margins, such as we observe in the central South Atlantic between Brazil and West Africa. So we can compare these models with these conjugate sections from Brazil and West Africa, and they basically exhibit very similar features, as we can see here. I'm going to skip this in the interest of time, and also because there is a plenary session in about 25 minutes, and we don't want to delay that. I'll just go very quickly over these. And so in summary, I've shown you some examples where we use forward models integrated with data from the Brazilian margin and its conjugates to understand controls on variation in structural style, on the degree of magmatic output and basin evolution, role of inheritance. We can also consider the oblique rifting in the Santos-Campos transition, and there are many more questions that I think we can address in this area, which is very interesting for science, and we hope also for exploration. Thank you. I'm not going to take any questions. Anybody interested in questions can come to me afterwards. It's quite unusual, but we have a very tight schedule. So the next speaker is Victor Sacek. discuss Victor Sajek from Sao Paulo University. Victor, please.
Thank you, Hitski, for this opportunity. So I will discuss about the connection between deep and shallow geodynamic process. And first of all, I will discuss about the thermal structure of the upper mantle. Here I show a snapshot of a numerical model that simulates the convection in the mantle. And here we can see the lithosphere, and here the asthenosphere, and variation temperature close to zero in the surface to almost 2000 Kelvin at the base of the upper mantle. But when we calculated the deviation from horizontally average temperature, we can see that the advection, the convection in the asthenosphere is mainly guided by subtle changes in the temperature. Nearly 100 degrees Celsius is enough to maintain the convection in the asthenosphere. And if we convert this contrast of temperature to density contrast, we obtain nearly 10 kilograms per cubic meter. And this is one order of magnitude smaller than the contrast between the density contrast between ice and water. So the convection in the asthenosphere is maintained by a small difference in density. But when we come to the surface, we have a huge difference in density. From the air, almost new density, to the crust with 2,700 kilograms per cubic meter. And additionally, the denser material is below the less denser layer. So this interface is very stable. And it's very difficult for the planet Earth to displace this interface upward or downward. So one efficient way to change this interface is changing the crystal thickness. But we know that if you want to uplift 1 kilometer the surface, you have to add 5 or 6 kilometers to the crust. So it's not a simple task for the planet Earth. So based on these ideas and the difficulty of the planet Earth to displace the surface, we will observe an example from the northeastern portion of Brazil, the Borborema province. And this is a region where we have a complex margin with a geometry with a three-dimensional margin. We have the connection between the equatorial margin and the eastern margin, and the geology is also very complex. We have the divergent margins here and the equatorial margin here, and also other aborted rifts in the interior of the continent. Here we have Potiguar, other smaller basins here, the Adaripe Basin, Jatobá and Tucano Basin, rifts that not evolved to divergent margins. And especially I would like to discuss about this basin, the Adaripe Basin. Here we have a picture of the Adaripe Basin. We have the plateau, the Adaripe Plateau. It's now nearly 1 kilometer above sea level. And here is the stratigraphy cross-section crossing the Adaripe Basin. And we have preserved in the Adaripe beautiful fossils of dinosaurs and pterosaurs too. And we have geological evidence that at least a part of this sedimentary package here, up to 800 meters above sea level, was in the late Cretaceous close to the sea level. So we have here the rifting phase, the post-rift phase, and we have preserved sediments 90 million years old, and then a certain moment after desedimentation, all this region was uplifted. So how can we explain the post-rift uplift of the Borborema province? And different mechanisms were proposed to explain the post-drift uplift. One of these mechanisms is magmatic underplating, thermal anomaly in the mantle, and regional horizontal compression. But receiver function data indicates that the crust is not so different from the rest of Brazil. So it's difficult to use the underplating to explain the uplift, the post-drift uplift of the entire region. Additionally, we have a clear mantle anomaly. This is the joint anomaly from the mantle, removing the contribution from the crust. We have, in fact, a negative anomaly here, but this is not enough to explain 1 kilometer of uplift. We can explain with this mantle anomaly a few hundred meters of uplift. So, but all these models don't take into account surface process. In fact, the surface of the Earth is not passively modified by the internal dynamic of the Earth, but can shape the surface by erosion and sedimentation. So in this presentation, I will show a numerical model that tries to couple interior dynamics of the Earth and surface process to study the evolution of this portion of the margin. So in this numerical model, I coupled stretching and faulting of the lithosphere, surface process, thermal process, and flexure and isostasy of the lithosphere. Surface process are simulated by fluvial dynamics, and I won't discuss about the details of the equation, but I would like to discuss about this parameter here, LF. Usually, this parameter that controls the erodibility of the rocks, most of all the numerical models are divided only in sediments and bedrocks. But here, to simulate the formation of the Adalip, which is capped by a Dury crust, I incorporated a weathering process that can turn a certain layer of the sedimentary package more resistant to erosion than the bedrock to simulate the evolution of the Adalip. And this hardening is controlled by the residence time that a certain sedimentary layer stay close to the water table. If this sedimentary layer stays for millions of years close to the water table, this layer becomes harder to be eroded than the bedrock. So I incorporated flexure, in which any load at the surface are partially compensated by the rigidity of the lithosphere and partially by the buoyancy exerted by the asthenosphere. And this is controlled by the TE, the effective elastic thickness. The larger the TE, more rigid is the lithosphere. Okay, and I simulated stretching and thermal effects, so I can take into account the isostatic effect, the flexural effect of stretching the lithosphere, and I created a map, a stretching map for the model using the beta factor. And I created a beta map. The larger the beta, the higher the magnitude of stretching of the lithosphere. And here is the model where I considered the divergent margin, the Potiguar Basin, the Adalip, Jatobá, and Tucano. It's a simplified model. And I studied different parameters, for example, initial elevation, effective elastic thickness, and precipitation that will control the rate of erosion. And in the standard model, I simulated the stretching that formed the margins, that uplifted the margin due to flexural effects. And then we have fluvial incisions and the deposition in the interior basins and offshore too. And with time, it's interesting that the erosion of adjacent regions of the Adalip Basin can induce the flexural isostatic effect of the entire lithosphere that can uplift the Adalip Basin up to more than 1 kilometer without imposing post-drift uplift, only due to differential denudation of the landscape. However, we have a geological constraint that in the Araripe you have nearly 600 meters of post-drift sediments preserved in the Araripe. And in these modules, where here I show each symbol represents a model with different effective elastic thickness, initial topography, and precipitation, in all these modules I couldn't simulate the observed thickness of post-drift sedimentation in the Araripe Basin. In a second set of experiments, I incorporated sea level variations. And with sea level variation, I increased the total post-drift sediment preserved in the numerical model close to the observed one, but the height of the plateau is smaller than the observed. And then in a final set of experiments, I incorporated a post-drift uplift of only 250 meters of post-drift uplift. And this is the simulation that I created. This is time in million years, and then we have this denudation. Then I imposed, in this simulation it was 400 meters. But here we can see the formation of the Araripe. I created cross-sections crossing the Araripe and Potiguar Basin to show the stratigraphic evolution. And here we can see the post-drift sedimentation, and then the post-drift uplift, and then scission and preservation of the plateaus here. We can see Inselbergs preserved here too, like this one. This is not in Brazil. And the amount of post-drift sediments preserved in the Araripe Basin is controlled mainly by the initial topography used in the numerical simulation. But in these simulations where I imposed only 250 meters of post-drift uplift, it was possible to explain both the altitude of the Araripe Plateau and the final thickness of post-drift sedimentation, showing this dark gray square here. It's important to see here the temporal evolution of the denudation of the margin. Here I show a cross-section in this direction here, where I simulated the denudation. It's the same model, and each layer here represents 1,500 meters of denudation. So here we have almost 2 kilometers. And with time, the maximum denudation migrates landward. And in the last 40 million years of simulation, we can observe that the maximum denudation occurs not close to the coast and not close to the interior basins, but in an intermediate position. And thermochronological data indicate this. We have the younger ages close to the Borborema Plateau in the interior of the continent, and these young ages are not observed in the margin and around the interior basins. And here I show the predicted fission track age in the numerical model in the map, and the dots represented observed data. And furthermore, it's interesting that due to the dirty crust formation, the timing of enhanced denudation is not directly related to the timing of uplift, but the denudation in part of the samples, part of the model, occurred tens of million years later than the moment of uplift due to the dirty crust preservation. And this can explain the cooling age observed in the Borborema province. Probably this protracted cooling history can be related to only one pulse of uplift, and the presence of this resistant layer to erosion created this complex history of cooling history of the rocks at the top of the basement. The conclusions of this model is that nearly 70% of the post-rift uplift in Borborema province can be explained by differential erosion and flexural rebound. And the remaining nearly 250 meters of post-rift uplift can be due to partial erosion of the continental lithospheric mantle. I didn't explore in details this aspect, but we can discuss later. Weathering is a key ingredient to explain the regional denudation pattern in the Borborema province, and the formation of dairy crusts at the top of the basement can induce protracted exhumation, creating a denudation pattern not directly correlated to the timing of regional uplift. Thank you very much.
Very nice, Victor. Any questions for Victor? Yeah, go ahead.
Exactly. Exactly. Yeah. In fact, in the numerical experiments, we can reach 4 kilometers of denudation. So the thinning process in most part of the Borborema can be explained by surface process. Okay, so this post-rift uplift of only 200 meters was the trigger to amplify the differential denudation. So what can explain the thin crust observed in this region can be denudation. Yeah, yeah. So other Inselbergs or other plateaus can be, because in the numerical experiment, yes, yes. In fact, these ones are fluvial deposits, not so. Maybe they can be explained by the same process, and we have dairy crusts not only in the sedimentary package but also in the bedrock. So this is a simplified model, but other plateaus and Serra do Martins, for example, can be explained in the same fashion.
So can you explain the plateau here further inland if you go?
Which one?
Well, basically if you go just inland here, at some point you go up escarpment and it's about.
No, here it's different because we don't have clear lithological control. Yeah, maybe part of post-rift uplift can be induced by erosion of the mantle, partial erosion of the lithospheric mantle. And these can preserve the escarpments high for more than 100 million years. It's possible that these mechanisms can. So these, so what is important is that the surface process are important to preserve the escarpment high, and not only the internal dynamics of the Earth. Okay. Thank you.
We ended in time, which is very nice because there's a plenary session starting in a few minutes. I'd like to thank all the speakers of today's session, which was very interesting, very broad range of topics. And I have to say I look forward to a successful collaboration to continue this. Good, thank you very much.
Just 1 second. Fabio Diaz, is he here? Maybe you